Welcome to the third session of this integration series. In this session, we will introduce the techniques of using the integral form of the chain rule or reverse chain rule, as well as substitutions. Based on these techniques, we will demonstrate the integrals with trigonometry and their inverse functions, along with composite functions through 8 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the third session of this integration series. In our first worked example, there are 3 antiderivatives to find. Here we are going to apply the technique of integration with composite functions. In question 1, since the antiderivative is written to the integral of x to the 4th minus 1, or in parentheses to the 5th times 1 over 4 times the differentiation of x to the 4th minus 1 dx, which can be further simplified to 1 over 4 times the integral of x to the 4th minus 1, or in parentheses to the 5th dx to the 4th minus 1, or in parentheses, which equals 1 over 24 times x to the 4th minus 1, or in parentheses raised to the power of 6 plus c. As for the second question, since the differentiation of 2x squared plus 1 with respect to x equals 4x, the antiderivative can be written to 1 over 4 times the integral of 1 over the square root of 2x squared plus 1 d2x squared plus 1, or in parentheses by dx, which equals 1 over 4 times the integral of 2x squared plus 1, or in parentheses to the negative 1 over 2 d 2x squared plus 1, or in parentheses, which equals 1 over 2 times the square root of 2x squared plus 1 plus c. In question 3, since the differentiation of e to the 3x plus 5 equals 3 times e to the 3x, the antiderivative can be written to 1 over 3 times the integral of square root of e to the 3x plus 5 times the differentiation of e to the 3x plus 5 dx, which is simplified to e to the 3x plus 5, or in parentheses to the 1 over 2 d e to the 3x plus 5, or in parentheses, which equals 2 over 9 times e to the 3x plus 5, or in parentheses to the 3 over 2 plus c. Now we're going to talk a little bit about the chain rule and substitutions. Since we have already familiar with the differentiation form of the chain rule, and based on that, we are now introducing its integral form. Suppose that the f is a function of u, which is in turn a function of x. Here the capital F, f of u, is a primitive function of f of u. Hence, differentiating the primitive function f of u with respect to x and applying the chain rule gives d dx of f of u equals df by du times du by dx. So d dx of f of u equals f of u times u prime. Then we integrate both sides of above equations, which gives the integral of d dx of f of u dx equals f of u plus c. Now in the second worked example, we are going to apply the integral form of the chain rule to a proved integral of sine x sine 2x dx equals 2 over 3 times the cubic of sine x plus c, according to sine double angle formula. sine 2x equals 2 times sine x cosine x. So sine x sine 2x equals 2 times the square of sine x times cosine x. Based on that, the differentiation of sine x is cosine x. d sine x equals cosine x dx. Hence, the left side of the equation equals 2 times the integral of the square of sine x cosine x dx, which equals 2 times the integral of the square of sine x d square of sine x, which equals 2 over 3 times the cubic of sine x plus c, which equals the right side of the equation. Example 3 is to find two antiderivatives. As for the first antiderivative, since the differentiation of cosine 2x equals negative 2 sine 2x, which implies that d cosine 2x equals negative 2 sine 2x dx. Hence, the antiderivative can be written to the integral of square root of cosine 2x times negative 1 over 2 times d cosine 2x by dx, which equals negative 1 over 2 times the integral of square root of cosine 2x d cosine 2x, which is negative 1/3 times the cubic of square root of cosine 2x plus c. As for question 2, since the differentiation of e to the x is e to the x itself, d e to the x equals e to the x dx. So the antiderivative equals the integral of sine e to the x d e to the x by dx, which equals the integral of sine e to the x d e to the x, which equals negative cosine e to the x plus c. Example 4 is to find two antiderivatives. As for the first one, since the differentiation of arcsine of x equals the reciprocal of the square root of 1 minus x squared, d arcsine of x equals the reciprocal of the square root of 1 minus x squared dx. Hence, the antiderivative equals the integral of e to the arcsine of x d arcsine of x by dx, which equals the integral of e to the arcsine of x d arcsine of x, which is e to the arcsine of x plus c. As for the second antiderivative, since the differentiation of ln of modulus of x equals 1 over x d ln of modulus x can be written to 1 over x dx. Hence, the antiderivative equals the integral of sine of ln of modulus x d ln of modulus of x by dx, which equals the integral of sine of ln of modulus of x d ln of modulus of x, which equals negative cosine of ln of modulus of x plus c. Here, example 5 is to find two antiderivatives. As for the first one, since the differentiation of e to the t squared plus 16 equals 2t times e to the t squared, the e to the t squared plus 16 equals 2t times e to the t squared dt. So the antiderivative is written to 1 over 2 times the integral of e to the t squared plus 16, or in parentheses d e to the t squared plus 16, or in parentheses by dt, which can be expressed to 1 over 2 times the integral of e to the t squared plus 16, or in parentheses d e to the t squared plus 16, or in parentheses, which is 1 over 4 times e to the t squared plus 16, or in parentheses squared plus c. As for question 2, since d dx of cosec x equals negative cosec x cotangent x, the antiderivative can be written to negative integral of the reciprocal of 1 plus the square of cosec x times d cosec x by dx, which equals negative integral of 1 over the sum of 1 and the square of cosec x d cosec x, which is arccotangent of cosec x plus c. Here we continue to work on the second antiderivative of example 5, and we will show you an alternative approach for this question. Since the integrand function can be transformed by multiplying the square of sine x on both numerator and denominator, it becomes cosine x over the sum of square of sine x and 1. Since we know that the differentiation of sine x is cos x, d sine x is written to cos x dx. Now let's go back to the antiderivative, since it can be written to 1 over the sum of the square of sine x and 1, d sine x by dx. It can be further expressed to the integral of 1 over the square of sine x plus 1 d sine x, according to the integral formula for inverse tangent function. The antiderivative equals arctangent of sine of x plus c. Example 6 is to find the antiderivative of the integral of the cubic of cos x over the square root of sine x dx. Since the differentiation of sine x is cos x, d sine x equals cos x dx. The integrand function of cubic of cos x over the square root of sine x is transformed to the square of cos x times cos x over the square root of sine x, which can be written to 1 minus square of sine x, or in parentheses times cos x over the square root of sine x. At this point, we let u equals sine x, hence du equals cos x dx. So the antiderivative can be written to the integral of 1 minus u squared, or over the square root of u du, which can be expressed to the integral of u to the negative 1 over 2 minus u to the 2/3, or in parentheses du, which equals 2 times u to the 1 over 2 minus 2 over 5 times u to the 5 over 2 plus c. After substituting back to the variable x, the antiderivative equals 2 square root of sine x minus 2 over 5 times sine x, or in parentheses raised to the 5 over 2 plus c. Example 7 is to find two antiderivatives using the integration form of composite functions. As for the first antiderivative, we let u equals the square root of sine x, which gives du equals cos x over 2 square roots of sine x dx, which can be written to the reciprocal of the product of 2 sec x and square root of sine x dx. Hence, the antiderivative is written to 2 times the integral of e to the u du, which equals 2e to the u plus c. After substituting back to the variable x, it equals 2 times e to the square root of sine x plus c. As for the second question, we let u equals the square root of 2x squared minus 1, which gives du equals 2x over the square root of 2x squared minus 1 dx. Hence, the antiderivative is written to 1 over 2 times the integral of sine u du, which equals negative 1 over 2 cos u plus c. After substituting back to the variable x, it equals -1/2 cosine open bracket square root of 2x squared minus 1 close bracket plus c. Example 8 is to find the antiderivative of the integral of sine 2x plus sine 4x, or in parentheses squared dx. Since the trigonometric function of sine 2x plus sine 4x, or in parentheses squared, can be expanded and then transformed from its multiplication form to the corresponding addition form. As it can be seen that 2 sine 2x sine 4x can be transformed to cos 2x minus cos 6x. Then the square of sine 2x can be written to 1 minus cos 4x all over 2, while the square of sine 4x can be written to 1 minus cos 8x all over 2. Hence, the integrand function of sine 2x plus sine 4x, or in parentheses squared, can be simplified to 1 plus cos 2x minus 1 over 2 times cos 4x minus cos 6x minus 1 over 2 cos 8x. So the antiderivative equals the integral of 1 plus cos 2x minus 1 over 2 times cos 4x minus cos 6x minus 1 over 2 times cos 8x, or in parentheses dx, which equals x plus 1 over 2 times sine 2x minus 1 over 8 times sine 4x minus 1 over 6 times sine 6x minus 1 over 16 times sine 8x plus c. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.